In 1299, the money changers of Florence adopted a rule for their guild. Members were not to keep their books in the new figures. Florence was one of the richest cities in Europe, and the money changers were among the richest men in Florence, bankers, in everything but name, financing wool merchants and popes and kings. These were not superstitious men frightened of foreign symbols. They were professionals protecting a professional standard, and what they had decided was that the numerals you are reading this sentence with were not safe to put in a ledger. Other cities and institutions took similar positions. For roughly 3 centuries, from the first arrival of the new system in Latin Europe to its final victory, there was an argument, sometimes technical, sometimes commercial, occasionally legal, about whether Europeans should adopt the digits that the entire world now uses. The obvious modern reaction is that the objectors were fools. They were not. They had a specific, concrete, and entirely correct concern, and I will get to it. But to see why the argument was real, you first have to stop assuming that the system Europe already had was rubbish. It wasn't. It was rather good. And almost nobody today understands how it worked, because we have inherited the winner's account. Picture a merchant in Genoa in the year 1200 needing to add up a column of figures. He does not do it on paper. Paper is scarce and expensive in Europe at this date, and in any case, that is not how you calculate. He does it on a board, a table with lines ruled across it, or a cloth marked out with rows, using small metal discs called counters, or jettons. The bottom line is units. The line above is tens. Above that, hundreds. You put out counters to represent a number, put out more for the number you are adding, and then you tidy up. Whenever 10 counters accumulate on a line, you sweep them away and put 1 counter on the line above. That is addition. It is fast, it is physical, it is nearly impossible to get wrong if you can count to 10, and it does not require you to be literate. Subtraction is the same in reverse. A trained clerk working a counting board is quick enough that in some head-to-head demonstrations, right through the 16th century, the counting board could beat pen and paper arithmetic on simple sums. Notice, too, that the counting board has place value. The lines are the columns. The bottom line is ones, the next is tens, and a counter's meaning depends entirely on which line it sits on. Europe had positional notation on the table. It just did not have it on the page. And it had a working zero, in exactly the way China did, an empty line. No counters here. Perfectly clear, perfectly functional, entirely unnamed. The Roman numerals were not the calculating system. They were the recording system. What you wrote down afterward in the ledger to say what the answer had been. Nobody was doing long division in Roman numerals, because nobody was doing any arithmetic in Roman numerals at all. They were a notation for storing results, and for that purpose they are perfectly adequate. And as we will see, they have one genuine advantage that the new digits do not. This whole apparatus goes back a long way, and we have already met a piece of it. Remember the English exchequer from Chapter 1, splitting hazel sticks lengthwise to record debts. Exchequer comes from the checkered cloth spread on the table, the ruled counting board. The chancellor of the exchequer is, etymologically, the man in charge of the counting cloth. Half of Europe's financial vocabulary is fossilized furniture. To count is to compute. A counter is both the disk and the surface you slide it on. And the thing at the front of a shop is called a counter, because that is where the money was reckoned. So, a functioning, fast, tactile system, thousands of years old, embedded in the institutions and the language. This is what the new numerals had to displace, and it is why the displacement took 300 years. Now, the boy. Around 1180, a Pisan official named Guglielmo was posted to Bejaia on the coast of what is now Algeria to represent the interests of Pisan merchants trading there. Pisa at this date was a maritime republic with a fleet and a commercial empire, and Bejaia was a substantial North African port. Guglielmo took his young son with him and, by the son's own account, arranged for him to be taught calculation, thinking it would be useful in business. What the boy was taught was the Hindu-Arabic system, the 9 digits and the 0, and the pen and paper procedures for working with them that Al-Khwarizmi had explained 3.5 centuries earlier. He described what happened next in the preface to the book he eventually wrote. He was captivated. And as he grew up and traveled on business, Egypt, Syria, Greece, Sicily, Provence, he made a point of studying how merchants and scholars calculated everywhere he went, comparing methods. He concluded that the system he had learned as a child in North Africa was better than anything else in use anywhere, and that Europe should have it. His name was Leonardo, and he was from Pisa, so he signed himself Leonardo Pisano. He was not called Fibonacci. Nobody called him Fibonacci. The name was invented in 1838, nearly 600 years after his death, by a French-Italian historian who appears to have coined it from Filius Bonaxi, son of Bonaxio, or from the family name. It stuck so thoroughly that it is now the only name most people know, attached to a sequence he did not discover from a problem he did not think was important, in a book that is mostly about currency exchange. We are going to have to work through that sentence in pieces. The book is the Liber Abaci, the Book of Calculation, first written in 1202 and revised in 1228. Its opening is one of the great understated sentences in the history of European thought. Leonardo announces the 9 figures of the Indians, lists them, and then adds that with these, and with the sign that the Arabs call Zephyrim, any number whatsoever can be written. Zephyrim. That is the Latinized cipher from chapter 7 on its way to becoming 0. You can watch the word cross the Mediterranean in that sentence. And then, having promised that any number can be written, he spends several hundred pages proving it, not with theorems but with business. The Liber Abaci is a commercial manual. It teaches you how to write the numerals, how to add, subtract, multiply, and divide them, how to handle fractions. Then it goes to work on the actual problems of Mediterranean trade in the 13th century, which were vicious. Every city had its own currency, its own weights, its own measures. A merchant moving goods from Pisa to Constantinople had to convert money at each stop, calculate customs, split profits among partners who had contributed unequal capital for unequal times, compute the value of alloyed coinage of uncertain purity, work out barter exchanges between goods with no common price. The book is full of this. How to divide the profits of a partnership, how much silver is in this coin, how many bushels of wheat for this many barrels of oil, how to price a shipment after freight and tax. It is, in other words, exactly what an ambitious merchant's son needed. And that is the whole point of this chapter. The new arithmetic did not enter Europe through the universities. The universities were doing a different kind of arithmetic entirely. A theoretical, philosophical subject inherited from Boethius and ultimately from the Greeks, concerned with the properties and ratios of numbers as a liberal art, beautiful and utterly useless for working out the customs duty at Alexandria. The people who needed to calculate were merchants. The people who adopted the new system were merchants. Mathematics came into Europe through the counting house, not the cathedral school, and it came because it made money. Somewhere in the third part of the Liber Abaci, among a great many other exercises, there is a problem about rabbits. A man puts a pair of rabbits in an enclosure. Each pair produces a new pair every month, beginning in its second month of life. None of them die. How many pairs are there after a year? Work it through and the monthly totals run. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233. Each number, once you are past the start, is the sum of the two before it. There it is, the most famous sequence in mathematics, and one of the very few pieces of pure mathematics that ordinary people can name. 3 things about it are worth saying, and all 3 are usually left out. The first is that in the Liber Abaci, it is a minor exercise. One problem among hundreds, sitting between other recreational puzzles, with no indication that its author thought it especially significant. He did not name it, did not develop it, and did not return to it. The sequence acquired its invented surname in the 19th century, when a French mathematician started calling it that. The second is that it was not new. Sanskrit scholars had found the same sequence centuries earlier from a question about poetry. Sanskrit verse is built from syllables of 2 durations. Short ones lasting 1 beat, long ones lasting 2. So a prosodist asks a natural question, in how many different ways can you fill a line of a given number of beats? For a line of 1 beat there is 1 pattern, For 2 beats, there are 2. For 3, 3. For 4, 5. For 5, 8. And you can see immediately why. Any pattern of n beats either ends in a short syllable, in which case the part before it is a pattern of n1 beats, or ends in a long one, in which case the part before it's a pattern of n2. So the count for n is the count for n1 plus the count for n2. That is the rule derived from meter, and it is exactly the rabbit rule. Indian writers on prosody had this well before Leonardo. The line runs back through Virahanka and others to Henson Pingala, centuries before the Common Era, and it is stated cleanly by Hemachandra around 1150, roughly 50 years before the Liber Abaci. Whether anything traveled west or the 2 discoveries were independent, nobody can say. But the sequence was in India first, found by people counting poems rather than rabbits. The third thing is that the rabbit model is biological nonsense, immortal rabbits, fixed breeding schedule, no predators, and Leonardo surely knew it. It is a puzzle, not a study of animals. None of which stops the sequence from being genuinely, deeply important. It just wasn't important for the reason, or to the person, or at the time that the story usually says. Because here is what the numbers actually do. Take any 2 consecutive terms and divide the larger by the smaller. 3 over 2 is 1.5. 5 over 3 is about 1.667. 8 over 5 is 1.6. 13 over 8 is 1.625. 21 over 13 is about 1.615. The results oscillate overshooting and undershooting, closing in on a single value, roughly 1.618. That number is the golden ratio, and we have met it before. It is the proportion hiding in the 5-pointed star, the badge of the Pythagorean brotherhood, the emblem they wore over their hearts, which turned out in Chapter 3 to be riddled with the same incommensurability that broke their worldview. The star-zone ratio coming back 1800 years later out of a problem about rabbits. And now the part that is genuinely wonderful and true, and usually told badly. Go and look at a sunflower head. The seeds are arranged in spirals, curving out from the center in both directions, and if you count the spirals, you will nearly always get 2 consecutive Fibonacci numbers, 34 one way and 55 the other, or 55 and 89. Pine cones do it with smaller numbers. Pineapples do it. The scales, the florets, the seeds, over and over, Fibonacci numbers in living tissue. The plant is not counting. Here is what is actually going on, and it ties this chapter back to the diagonal of the square in a way I find close to miraculous. A growing shoot tip produces new buds one at a time, each rotated by some fixed angle from the last. The question the plant's geometry has to solve is, what angle gives the best packing? If the angle is half a turn, every third bud lands on top of the first, and you get 2 crowded rows with empty space between. If it is a third of a turn, you get 3 rows. Any angle that is a simple fraction of a full turn produces alignment, buds stacking up in spokes, wasting space, and shading each other. To avoid alignment forever, you need an angle whose fraction of a turn is not simple. Not a nice fraction at all. In fact, you want the number that is hardest to approximate by any fraction, and there is such a number, and it is the golden ratio. In a precise mathematical sense, phi is the most stubbornly irrational number there is. Every other irrational can be pinned down surprisingly well by some fraction with a modest denominator. Phi resists this more than anything else. So a plant that puts out each new bud at the golden angle, about 137.5 degrees, which is a full turn divided in golden proportion, never repeats, never aligns, and packs its seeds more evenly than any other rule would. And because the angle is golden, the spirals that the eye picks out come in Fibonacci counts automatically as a consequence. Which means the irrationality that horrified the Pythagoreans, the property of being unreachable by any ratio, the thing that made them call such numbers unspeakable, is precisely the property that makes sunflowers work. Nature did not choose phi despite its irrationality. It chose phi because of it. The monster is what makes the flower. Now the debunking, because you have heard the other claims and most of them are false. You have probably been told that the golden ratio governs the proportions of the Parthenon, the Great Pyramid, the Mona Lisa, the human body, the Nautilus shell, and the compositional grid of Renaissance painting. That it is a universal law of beauty, known to the ancients, hardwired into the eye. Very little of this survives inspection. The Parthenon claims depend on where you decide the rectangle's edges are, and by moving the boundaries, you can extract almost any ratio you like from any building. There is no ancient text connecting the golden ratio to the Parthenon, to the pyramids, or to any principle of beauty. The Greeks who wrote about it, including Euclid, treat it as a geometric construction, not an aesthetic one. Leonardo da Vinci illustrated a book about it, but there is no evidence. He composed paintings around it. The Nautilus shell is a logarithmic spiral, which is real and lovely, but it is not the golden spiral, measure a few, and you get ratios scattered well away from 1.618. The idea that phi is the key to beauty is essentially a 19th century invention, propagated by a German psychologist and popularized until it became common knowledge, after which people went looking and, as people always do, found it. Some 20th century artists and architects genuinely did use it, Le Corbusier and Dalí among them, but they used it because they had read the myth. I labored this because the sunflower is real and the Parthenon is not, and the difference matters. One is a mathematical fact about packing that has a mechanism you can explain and a prediction you can test. The other is pattern hunger, the same appetite that read prime numbers into the Ishengo bone in Chapter 1. A small set of numbers will always contain patterns if you are hungry enough to find them. Being able to tell the two cases apart is most of what it means to think mathematically, and the golden ratio is the best place in this book to practice. So, back to Florence and the ban, and the objection I promised was a good one. Roman numerals have a property that the new digits lack. They are extraordinarily hard to falsify. Look at what it takes to alter a number written as XIII. You can add strokes to make it XIIs, but that is about it, and it will look obviously crowded and wrong. Roman numerals are built from repeated marks, and the shapes are distinct enough that turning one into another is conspicuous. Better still, medieval ledgers often wrote sums out in words, which cannot be doctored at all. Now look at what it takes to alter a 1. A single stroke makes it a 7, or a 4, or a 9. A 0 becomes a 6 or a 9 with one curl of the pen. A 3 becomes an 8. And because the system is positional, a single added digit at the end of a figure multiplies it by 10, one stroke of a pen turning a debt of 30 into a debt of 300. The bankers of Florence were not resisting the future. They were running a fraud control regime, and they had noticed, correctly, that the new notation was dramatically easier to forge. This is precisely the kind of objection that gets left out of the story when we tell it as enlightenment versus superstition, and precisely the kind that people who work with money actually raise. They were also, as it turned out, on the losing side, and here is why. The counting board is superb at adding and subtracting and terrible at everything else. Try multiplying 347 by 158 with counters, and you will find yourself doing repeated addition and losing track. Long division is worse. And as European commerce grew more sophisticated, interest, partnerships with unequal shares, currency arbitrage, insurance, discounting a bill of exchange, the calculations that mattered stopped being sums and started being multiplications, divisions, and proportions. And the board has one crippling flaw as a business instrument. When you sweep the counters away, the working is gone. There is no record of how you got the answer. Nothing to check, nothing to audit, nothing to show a partner or a court. Pen and paper arithmetic in the new digits leaves a trail, every carry, every partial product, sitting on the page where a second person can follow it. For a family firm with branches in 4 cities, correspondents in a dozen more, and partners demanding an accounting, an auditable trail is not a convenience. It is the whole business. The transmission happened through schools, and hardly anyone has heard of them. From about 1300, Italian cities filled up with Abbaco schools, small, private, vernacular institutions, where a master taught the sons of merchants to calculate. Not Latin, not theology, not the liberal arts. practical commercial arithmetic in everyday Italian, aimed at boys of 11 or 12 who would be running a warehouse in 5 years. Hundreds of these schools operated. Thousands of their manuscript textbooks survive. That is the real machinery of the change. Leonardo's Latin book was influential among the learned, but what actually converted Europe was 2 centuries of teenagers being drilled in the new digits because their fathers were paying for it. The bookkeeping followed. In 1494, a Franciscan friar named Luca Pacioli published a vast printed compendium of everything the Abbaco tradition had accumulated. And tucked inside it is the first printed description of double-entry bookkeeping, the system of recording every transaction twice as a debit and a credit, so that the books must balance and an error announces itself. It was not his invention. Venetian merchants had been doing it for a century. But printing it made it standard, and double entry is one of the great intellectual technologies. An error-detecting code invented for money 300 years before anyone thought of error-detecting codes. Pacioli also wrote a book on the golden ratio, illustrated by his friend Leonardo da Vinci, which is a large part of why the golden ratio myth attached itself to Leonardo in the first place. And then printing settled the whole question. Once arithmetic textbooks were being printed by the thousand, the shapes of the digits stabilized. Before that, handwritten forms varied enough that a 4 or a 5 from one region could be unreadable in another. And the new system stopped being a foreign import and became simply how arithmetic is written. There is a woodcut from 1503 that captures the transition with unusual clarity. It shows 2 men at their calculations. Boethius, using the new numerals, working confidently on paper. Pythagoras, hunched over a counting board, looking distinctly unhappy. Between them stands arithmetic personified, her dress embroidered with the new digits, and she has turned toward Boethius. It is not a neutral illustration. It is an advertisement, printed while the argument was still going on, and it is worth remembering that the people who made it did not yet know who would win. One last thing about Leonardo, because he deserves better than rabbits. Around 1225, the Holy Roman Emperor Frederick II, a genuinely strange and brilliant monarch who kept a menagerie, spoke 6 languages, and was known to his contemporaries as the wonder of the world, held court in Pisa, and Leonardo was presented to him. A member of the imperial entourage said him challenge problems in front of the emperor in what amounted to a mathematical tournament. One asked for a rational number whose square, when you add 5 and when you subtract 5, gives a square in each case. Leonardo produced 41/12 and could show why. Another was a cubic equation. He demonstrated that it had no solution of the simple kinds available, and then gave a numerical approximation in sexagesimal notation, accurate to something like 9 decimal places, without a word about how he got it. Nobody has ever fully reconstructed his method. He also wrote, that same year, a treatise called The Book of Squares, which is first-rate number theory, inventive, difficult, and the best pure mathematics produced in Europe for centuries on either side of it. It was largely ignored. 15 years later, the city of Pisa granted him a salary in recognition of his services in accounting and instruction. The practical arithmetic paid. That is the shape of his reputation in miniature. His deepest work vanished into obscurity. His commercial manual changed the continent. And the thing that made him a household name 800 years later was a throwaway puzzle about rabbits, which had been discovered in India first, and which now carries a surname invented for him by a historian in 1838. By 1500, the argument was effectively over. Europe had the numerals, the zero, the algorithms, the algebra, decimal arithmetic, double-entry books, and a printing press to spread all of it, an inheritance assembled in Babylon, China, India, and Baghdad. Delivered by merchants and translated by scholars, and about to be handed to a continent that was, at that exact moment, developing an appetite for the impossible. But before we go there, we have some unfinished business with the story I have just told, and it is uncomfortable business. Because in the same centuries, a Persian poet was solving cubic equations with intersecting conic sections and building a calendar more accurate than the one you are using. And in a village in southern India, a school of mathematicians was summing infinite series to calculate pi, deriving results that Europe would celebrate as the discoveries of Newton and Leibniz and Gregory. 300 years before those men were born. The next chapter is about them. It is also about what it means to say that someone discovered something first, and why that question is a great deal harder and a great deal more political than it sounds.